Okay, cool. This is going to be an overview of the 3 AP FRQs that I assigned today on Monday, April 3rd. I don't know why it took me so long to think about it. Okay, now these 3 FRQs are going to be really helpful to review before your test, which will be next week. You don't have to watch the video now, but tonight, but what I do recommend is looking at it at some point before your test. You may or may not see some very similar FRQs on your test because they are great questions that tie together simple harmonic motion with stuff we've learned before in BFPM, MTM, ETM, all that good stuff. All right, so let's take a look at the first question. This first question is mild. What I've done is just redrawn it on another piece of paper so we can see it a little bit easier. All right, so we have a 0.2 kilogram mass sliding on a horizontal frictionless air track, which is represented with the blue over here, the speed of 3 meters per second when it instantaneously hits and sticks to this 1.3 kilogram mass initially at rest. Now the 1.3 kilogram mass is connected on one end to a massless spring, which is connected to one end of a massless spring, which has a spring constant of 100 Newton meters. So one end of the spring is fixed. So literally it's just going to stick and then it's going to oscillate at this point. So we need to find the linear momentum of this 0.2 kilogram mass before the impact as well as its kinetic energy. This is light work. We have P is equal to M times V. We know the mass is 0.2. This is A1, and we'll do A2 below it. P is equal to M times V. The mass is 0.2 kilograms. The velocity is 3 meters per second. So we should get a momentum of 0.6 kilogram meters per second. Now we need to find the kinetic energy, which is 1/2 mv squared, which is 0.5 times the mass, which is 0.2 kilograms, times v squared, 3.0 meters per second squared, is equal to, I believe, around 0.9 joules. Yeah, 9 times 0.1. Cool. 0.9 joules. All right, now we need to determine the following for the combined masses immediately after impact. For the combined masses, we need to find the linear momentum as well as the kinetic energy. All right, cool. Now, here's the thing. For the combined masses, we know that due to the conservation of linear momentum, the total momentum before the collision is going to be the exact same as momentum after collision. So the linear momentum should be the same before the collision as it is after the collision. P should be the same. Momentum will always be conserved. This is 0.6 kilogram meters per second, as it is for the little block before it hits the big one. Okay. Now, knowing this, however, we have to calculate what the kinetic energy is for the combined masses immediately after impact. This is just an inelastic collision, so let's get it. We got to find the velocity first of the whole mass system moving together. Okay, so initially I'll use M1 and M2, and then V1 and V2. So those are our labels. All right, so initially the only thing that's moving is M1. So we get M1 V1 is equal to, there's no momentum for that guy over there. So he has all the momentum, and they stick together is equal to M1 plus M2. Because they stick together, it's an inelastic collision, and they move with one final velocity. The final velocity is just equal to mass 1, which is 0.2 kilograms, times V1, which is 3 meters per second. So the initial momentum divided by the sum of the two masses. So we got 0.2 plus 1.3 kilograms. That should give you 1.5 kilograms. So we know that the final velocity of both of the blocks moving together, or the velocity of both the blocks moving together, should be 0.2 times 3 divided by 1.5, 0.4. So 0.4 meters per second. Now let's see how this stacks up for the kinetic energy, because we're going to use this to figure out what the kinetic energy is. So the kinetic energy is 1/2 mass of both of these things together, right? So now we're looking at this 1.5 kilogram object, technically, that's moving together, with a velocity of 0.4 meters per second. that gives us a kinetic energy of around 0.12 joules. So here it's 0.12 joules. Yeah, it was an inelastic collision. It seems like the kinetic energy has decreased from 0.9 joules to 0.12 joules. That it makes sense. In an inelastic collision, kinetic energy will go down. So Ke has decreased. Some energy has been released in the form of heat or sound. Okay. Now, that's all momentum. For part C and part D, after the collision, the two masses undergo simple harmonic motion about their position at impact. So if these two masses are undergoing simple harmonic motion, we have some information about the initial kinetic energy. We can determine what the amplitude of the harmonic motion should be based off of the conservation of energy. So over here, we know that, and I'll do energy in red. Why not? So here we have some kinetic energy. As soon as the blocks combine, they're moving with some kinetic energy. We know that that's going to convert into spring potential energy. So we have an equivalency here. You know, 1/2 mv squared. So Ke, all of the kinetic energy initial will go into all of the potential energy of the spring. And so from there, we know this Ke. We know what little k is right there, and we want to figure out what x is, because x is going to be the amplitude. All of that kinetic energy will go into compressing that spring, a particular displacement from equilibrium position. That displacement from equilibrium position will be the amplitude. So let's set that up right over here. I'll use the back of this piece of paper. So you got 1/2 mv squared is equal to 1/2 kx squared. We know that this right over here is actually 0.12 joules, and we know that K is actually 100 newton meters. So if I'm solving for x squared, I know that x squared is equal to 0.12 joules divided by 50. .0024, and then I got to take the square root of this whole thing, right? So the x is equal to then, wow, the square root of that. So we get around 0.0489 or 0.05 meters. That's the amplitude. That's how much this spring over here is going to compress, and that's how much it's going to go back out and compress and go back out and all that good stuff. Alright, max displacement x, 0.05. Now we need to figure out the period of the harmonic motion. We'll do the period in purple, because purple period, you know. So t, we're always going to use this expression. T is equal to 2 pi square root of m over k. This is a period of a spring. Now we know that as long as we have the spring constant, all we need is the mass, and in fact the amplitude does not make a difference. So if we have the mass of the simple harmonic oscillator, this is easy money. 2 pi square root of m. In this case we take the combined mass of the two blocks together, so that's 1.5 kilograms divided by k, which is 100 newton meters. If I do some fancy schmancy algebra, I will see that the period is then 0.77 seconds. Alright? That is all you have to do for the first FRQ. Let me know if you have any questions on that. Now let's take a look at the second FRQ. This is the first. So you should definitely, if you haven't done this one yet, give it a shot on your own. Definitely pause it. Pause the video now, don't watch the rest, give it a try, and then come back and finish watching the video. Okay. So the question poses a situation where you have a little ball of clay being dropped on a ideal massless spring, or pan suspension. That is, the pan suspension itself is suspended by an ideal massless spring. So basically, we drop it from a height. What happens, right? And we know we want to first figure out the speed of the clay before it hits, the instant it hits the pan. We want to figure out the speed of the system as just after they collide and stick together. Then we need to figure out what the spring constant is of the whole of this spring right over here, based off of the information we have from their collision, and then find the resulting period. Okay. I already know that A and B are going to be pretty easy money, but then C is where things are going to get a little tricky, and then D, oh, we got that. All right, let's take a look. Start out with A. Determine the speed of the clay the instant it hits the pan. Oh, we have a height right over. Oh, this should be drawn a little bit better, but assume that it was dropped from the actual height h. mgh is equal to 1/2 mv squared. Conservation of energy, easy money. So mgh is equal to 1/2 mv squared. Right? That's all we got to do here. Solve for velocity, square root of 2gh. Boom, you're done. All right, part B. That's how we find its velocity the instant before it hits the pan. Now for part B, it's a little bit different, or we have to use conservation of momentum, right? So that's an inelastic collision. This big mass is going to stick with, or they're both the same mass. This clay is going to stick with the pan, so we're going to have another inelastic collision. So I'm going to call this M. MV I is equal to 2M, because we know that it's M plus M, right? They have the same mass, so this actually makes it pretty convenient. So 2M, so the masses of both of the things together, times the final velocity, right? So the final velocity is going to be equal to mvi over 2m. So that is going to be just vi, which is the square root of 2gh. That's the speed of this before it collides. So the square root of 2gh over 2. Cool. Now we need to find the spring constant. If we know that this entire system comes to rest at a distance h over 2 below the current position. So they stick together, and then what happens is that this system with the pan must go down a little bit, down to a height of, let's draw it out, h over 2. It'll come down to here. So this entire thing will move down. Height h over 2. Okay. So where does that leave us? If we want to figure out the spring constant and we know the amount of energy here, then one really effective way to approach this is conservation of energy. Now, conservation of energy is going to be great because what we can do with conservation of energy is not only figure out, let's set it up first and see where that gets us. So conservation of energy gives us that the speed of the kinetic energy of the clay is right before it hits plus the potential energy of the system right before it hits is going to be equal to 1/2 kx squared. Alright, let's do it. So 1/2 mv squared plus mgh is equal to 1/2 kx squared. So we know that this energy, this kinetic energy right over here, plus this potential energy is going to be equal to the spring potential energy. So now we have the mass is going to be the combined mass of these two moving as soon as they hit, and then this mass over here is going to be the combined mass of both of those objects following this height, h over 2. X is also going to be h over 2. We have all this stuff. Alright, so let's do some substitutions. Definitely should not have taken this down where I did. Or drawn in the line where I did. Let me grab a piece of paper. I'll do this one right over here. Okay. So we want to solve for k. So k is equal to, we're going to multiply everything on the other side by 2, so, oh man, it's a lot of algebra. 2mv squared plus 2mgh And then we also want to get rid of this x squared, so we'll put it all over x squared, right? So multiplied everything by 2, and then divided by x squared. Cool. So now m, in this case, is actually the mass of both of these objects. So that's 2m times v squared. V squared is this whole guy over here. So square root of 2gh over 2 squared plus 2. M is then going to be times 2m, because all of the m's here are equal to 2m, because it's the mass of both the pan and the clay ball. 2 times 2m times g times h over 2. Right. We also know that this is all going to be over x squared, which is the same as the height, which is h is equal to, or x is equal to h over 2. Oh man, we got a lot of algebra right now. So then you get 2m times 2gh over 4 plus 4m mgh over 2 all over h over 2 squared. So let's start to cancel things out. 4, so that's 4, that gets rid of that. mgh plus 2mgh. So mgh plus 2mgh over h squared divided by 4. So that's 3mgh. 3mgh. Oh my gosh, so much algebra. 3mgh h squared over 4 is then equal to 3mgh over h squared divided by 4 is then equal to 12mgh over h squared, which then becomes 12mg over h. And that is your final answer. Yeah, so I mean, it is conservation of energy, but it's also conservation of algebra. Lol. Alright, that's what K is. Now, I just went ham with that algebra. For part D, and I'm going to do this on the sticky note because I don't have enough space on my actual piece of paper. D, we want to figure out the tension. Or sorry, the period of the oscillation. What am I saying, tension? The devil's wrong with me. So then the period is then equal to 2 pi square root of m over k. Well, we just solved for k. Would you look at that? So then it's equal to 2 pi divided by the mass of the entire system, which is 2m divided by k, which is h 12 mg. Cancel out the m's. We got 2 pi over h over 6g. That's a period. So the period is based solely on the mass and the spring constant. The mass is the combined mass of the ball and the pan, and the spring constant is what we solved for in the previous problem. Alright, this is kind of spicy. It's kind of spicy. Alright, so then K is equal to 12 mg over h, and then D is equal to 2 pi times the square root of h over 6g. Okay, now on to the last problem that we have to do. Alright. Now, for this problem in particular, things get pretty funky. We got an ideal spring of unstretched length, 0.2 meters, placed on horizontally on a frictionless table as shown above. So, no friction. One end of the spring is fixed and the other end is attached to a block of mass m is equal to 8 kilograms. The 8 kilogram block is also attached to a massless string that passes over a small frictionless pulley. A block of mass m is equal to 4 kilograms hangs from the other end of the string with the spring. When the spring and block system is in equilibrium, the length of the spring is 0.25 meters and the point And the 4 kilogram block is 0.7 meters above the floor. All right, so one thing that I'm going to do immediately is take note of where this block is relative to the spring. So we know that this height is labeled for us 0.7 meters. The mass is 4 kilograms. It's suspended 0.7 meters above the floor. But this is not labeled for us on the picture. What we know is that the unstretched length of this spring is 0.2 meters. We know that it's 0.2 meters unstretched. Now, in this case, we also know that when the spring and block system is in equilibrium, the length of the spring is 0.25 meters. So that tells us that from rest position, the displacement is 0.05 meters. So delta x, right over here, 0.25, or right, so delta x is equal to 0.05 meters, because it's the difference between stretched and unstretched, 0.05 meters, right? And that's just going to be a label that we put on this first one, on the figure. All right, now the first part is asking us to draw some free body diagrams. We can do that. So the FBD for the 8 kilogram mass, we got some force of gravity, we got some normal force, we got some tension, and we have an FSP, spring force. Cool. Now for the 4 kilogram force, or 4 kilogram mass, we have some F sub G, and we have some tension. All right. Now we want to calculate the tension of the string. Oh, easy money. Let's go back to BFPM. Fy is equal to Fg minus T. Is this object moving up or down? The answer is a resounding no. Therefore, Fg is equal to T. Therefore, the tension is going to be equal to the force of gravity, which is around 40 newtons, or let's say 40 newtons. Let's say that G is 9.8. Cool. Now that was part A, and that was part B. Calculate the force constant of the spring. Now we're getting somewhere. We're getting somewhere useful. Because if we want to calculate the force constant here, we know that the tension throughout this force constant right over here, one way of doing that is by finding the spring force itself. And we know that the spring force is up here on this big mass, 8 kilograms, and we know that it must balance out the tension. And since we just solved for the tension, and the tension must be the same throughout the string, let's do another net force equation. Say that FSP plus, I should have done that, Fx is equal to FSP plus Ft is equal to 0. In this case, these are in opposing directions, so we'll say that FSP is equal to negative Ft. FSP is also equal to K times X, and that's going to be equal to negative force of tension. So then K will be equal to negative 40 newtons over the displacement. In this case, the displacement is going to be negative. I messed up in the directions here, but K will always be positive, the displacement might be negative. So 0.05 meters. I should have made this, I should have made the tension positive and the spring force negative by drawing in the directions, but whatever. So we'll say that K is going to be equal to whatever 40 divided by 0.05 is. 40 divided by 0.05. Around 800 newton meters. K is equal to 800 newton meters. Boom. The string is now cut at point P. So it's cut, and so now this starts to fall and this starts to oscillate. All right. So calculate the time taken by the 4 kilogram block to hit the floor. I'm doing this bad Larry on a sticky note. So this is interesting because for this part we know that for part D, this is just a kinematics question, right? The time taken for the block to hit the floor, when you have for this mass right over here, Mass does not matter. The only thing that's accelerating it is gravity. So what we got here? We got delta x is equal to 1/2 gt squared. It starts from rest, it follows a distance, boom, let's find t. So t is equal to 2 times delta x, this times the square root of g, or divided by the square root of divided by g, the square root of. Okay, cool. Square root of 2 times delta x is 0.7 meters, divided by 9.8. So when we do all the math, we end up with 0.37. So we'll say t is equal to 0.38 seconds. Cool. So that's part D. Now calculate the frequency of the oscillation by the 8 kilogram block. Calculate the maximum speed attained by the 8 kilogram block. All right. I'm going to put this right over here. All right, so we want to figure out the frequency of oscillation of the 8 kilogram block. We've done plenty of problems where we find the tension. Or, oh my gosh, the period. 2 pi times square root of m over k. It's the same thing, but we just want to find the inverse of the period. That's the frequency. In this case, once we find the period, we'll be able to find the frequency. The mass of the 8 kilogram block is 8. And the spring constant, as we figured it out, was 800. The period is therefore 2 pi times the square root of 8 divided by 800. 0.628. That is the period. Whoa! But that's not the frequency, because the frequency of loss is 1 over that. So 1 over 0.628 is going to be equal to 1.59 hertz. The frequency will be 1.59 hertz. Now, the final question that we're asked to solve is part F. Calculate the maximum speed attained by the 8 kilogram block. We know what this max spring potential energy is. We know that that is going to be equal to the max kinetic energy, 1/2 kx squared. It's equal to 1/2 mv squared. Whenever you want to find speed, max speed, you know that you can use the spring potential energy as a powerful tool to figure this out. Let's get rid of those 1/2s. Let's divide this by m, and then also take the square root of it. Okay, so boom, boom. To get the v by itself, I'm going to do some algebra. Never stop doing algebra. Alright, so v is equal to the square root of kx squared over m. K in this case, as we figured out, was around 800. X squared, the max displacement in this case was 0.05. Divided by the mass of the 8 kilogram block, which is 8. So v will be 2.23. Wait, that doesn't look right. Let me double check that that's right. Why doesn't it look right? The mass is 8 kilograms. Is it oscillating at 0.05? Yeah, okay. Yeah, well, that's what I got. Yeah, so let's go with it. V is equal to 2.2 meters per second. Alright. Very well. Y'all have a blessed day.